We are all familiar with chemical reactions via chemical equations.
We have here the reaction of hydrochloric acid and sodium hydroxide to form water and sodium chloride. Recalling back, the substances on the left side of the arrow are called the reactants or the inputs, while those in the right side are called the products or the outputs. The arrow shows us that a reaction has taken place. The plus signs separate the compounds or elements involved in the reaction. Let's have another example. We have here the reaction of two gases, namely oxygen and hydrogen. If you notice, there are numbers beside hydrogen and water. These coefficients stand for the number of molecules needed to perform the reaction. It is very important to balance chemical equations. Whatever is found in the reactant side must also be found on the product side.
So you might say it's easy to understand chemical equations. Well,
can you understand these? Or these?
My name is Rewey, and today we will talk about organic reactions. We will start first with the straight chain hydrocarbons. We have learned that there are three types of hydrocarbons:
alkanes with single bonds, alkenes with double bonds, and alkynes with triple bonds. Let's begin with chemical reactions involving alkanes. One of the most common reactions undergone by alkanes is combustion, where these hydrocarbons react with oxygen to release carbon dioxide and water. This is true for all alkanes. Whether it is butane or decane, the products are always carbon dioxide and water. Let's have the combustion of methane. As what I have mentioned earlier, the products are always carbon dioxide and water. Aside from that, you notice that there is a numerical value in the product side. That is called the heat of combustion, or the amount of heat liberated by the reaction. Combustion of methane releases 212 kilocalories per mole of heat. And always don't forget to balance the reaction. Now let's have the combustion of propane. Again, the products are carbon dioxide and water, and the heat of combustion is 530 kilocalories per mole. Then balance the equation. Another common reaction is halogenation, where halogens, usually bromine and chlorine, are reacted with alkanes. Let's have methane again. In this equation, we see that methane reacts with molecular chlorine, but we need to heat the mixture to at least 100 degrees Celsius or higher, as there will be no reaction that will occur if both substances are in cooler or room temperature. The products of the equation are chloromethane and hydrogen chloride. On the reactant side, you saw that methane has 4 hydrogen atoms, but on the product side, 1 hydrogen separated, and also the 2 chlorine atoms got separated as well. What happened was a double replacement reaction. Now we let chloromethane react with more chlorine, and the products are dichloromethane and hydrogen chloride. Another double replacement reaction has taken place. Now pause the video and try solving this problem. Now we'll go to alkenes. First, we have hydrohalogenation, or the addition of hydrogen halides, such as hydrogen chloride, hydrogen bromide, and hydrogen iodide. Addition of hydrogen chloride to ethylene, for example, gives chloroethane. If you notice that the double bond of the ethylene turn into a single bond in the product side, this is due to the addition of chlorine atom from hydrogen chloride. Addition of hydrogen chloride to propene gives 2-chloropropane. Hydrogen adds to carbon 1 of propene and chlorine adds to carbon 2. Why not the other way around? Well, according to Markovnikov's rule, in the addition of HX, where X is a halogen to an alkene, hydrogen adds to the double bonded carbon that has the greater number of hydrogens already bonded to it. Halogen adds to the other carbon. Now pause the video and try solving these problems. Next we have acid catalyzed hydration. In this type of reaction, this uses concentrated sulfuric acid as catalyst, and water adds to the carbon-carbon double bond of an alkene to give an alcohol, just like in this given equation involving ethylene. Here's another equation involving 2-methylpropene. If you look closely in the product side, it still follows Markovnikov's rule. Now pause the video and try solving this problem. In halogenation, the reaction is similar to that with the alkenes. In addition, that the double bond becomes a single bond in the product side, just like in this equation here. And unlike alkanes, halogenation in alkenes can occur in room temperature. Now let's have a cyclohexene react with molecular bromine. In the product side, the double bond of the cyclohexene is replaced by 2 bromine atoms. Now pause the video and try solving these problems. Next is hydrogenation. Virtually, all alkenes react quantitatively with molecular hydrogen in the presence of transition metal catalysts such as platinum, palladium, ruthenium, and nickel. In this reaction of trans-2-butene with molecular hydrogen, there is a conversion of alkene to alkane in the presence of a catalyst under certain conditions, which is why it is sometimes called catalytic reduction. Same goes also with the reaction of cyclohexene with molecular hydrogen. The metal catalyst takes the form of a finely powdered solid. The reaction is carried out by dissolving the alkene in ethanol, adding the solid catalyst, and exposing the mixture to hydrogen gas at pressures ranging from 1 to 150 atmospheres. The reaction of alkynes is similar to that of alkenes. They also undergo hydration, halogenation, hydrogenation, and hydrohalogenation.
So that is how straight-chain hydrocarbons undergo different reactions. But let's explore and go further with this topic.
What if you're given reactions involving benzene and its derivatives? One of those is halogenation. Under normal circumstances, benzene does not usually react with halogens unless there's a presence of an iron catalyst, just like in this equation here where benzene reacts with molecular chlorine to form chlorobenzene. In nitration, we heat benzene with a mixture of concentrated nitric acid and sulfuric acids, which would then replace one of the hydrogen atoms into a nitro group similar to this equation. While in sulfonation, heating an aromatic compound with concentrated sulfuric acid results in formation of an arenosulfonic acid, just like in this equation here, where the product form is benzene sulfonic acid. A major use of sulfonation is in the preparation of synthetic detergents.
Now you have learned the different reactions undergone by benzene and its derivatives. This time, let's include the functional groups.
Let's begin with alcohols with the functional group OH. One characteristic reaction of alcohols is its acidity. Alcohols are weak acids just like phenol, which reacts with aqueous sodium hydroxide to form sodium phenoxide. We can convert an alcohol to an alkene by eliminating a molecule of water from adjacent carbon atoms in a reaction. Primary alcohols like ethanol generally require heating in concentrated sulfuric acid at temperatures as high as 180 degrees Celsius. Primary alcohols are the most difficult to dehydrate. Secondary alcohols like cyclohexanol undergo acid-catalyzed dehydration at somewhat lower temperatures. Tertiary alcohols like tert-butyl alcohol generally undergo acid-catalyzed dehydration at temperatures only slightly above room temperature. Now pause the video and try solving these problems. A primary alcohol can be oxidized to an aldehyde or to a carboxylic acid depending on the experimental conditions. Following is a series of transformations in which a primary alcohol is oxidized first to an aldehyde and then to a carboxylic acid. The letter O in brackets over the reaction arrow indicates that each transformation involves oxidation. The reagent most commonly used in the laboratory for the oxidation of a primary alcohol to a carboxylic acid is potassium dichromate dissolved in aqueous sulfuric acid. Using this reagent, oxidation of 1-octanol gives octanoic acid. This experimental condition is more than sufficient to oxidize the intermediate aldehyde to a carboxylic acid. Secondary alcohols may be oxidized to ketones by using potassium dichromate as the oxidizing agent. Menthol, a secondary alcohol, is oxidized to menthone. Menthol is found in peppermint and is used in liquors, cigarettes, cough drops, perfumery, and nasal inhalers.
Tertiary alcohols resist oxidation because the carbon bearing the OH is bonded to 3 carbon atoms, therefore cannot form a carbon-oxygen double bond.
Now pause the video and try solving these problems. Amines are another type of organic compound, but this time their functional group is NH2.
The most important chemical property of amines is their basicity.
Amines react quantitatively with strong acids to form water-soluble salts as illustrated here. Now pause the video and try solving these problems. Then we have aldehydes and ketones. This diagram shows their differences in structure. Now let's have the different reactions. Oxidation. Aldehydes are oxidized to carboxylic acids by a variety of oxidizing agent including potassium dichromate, as shown in the equation below. Aldehydes are also oxidized to carboxylic acids by the oxygen in the air, as given in the equation. Now pause the video and try solving these problems. Reduction. Aldehydes are reduced to primary alcohols with the presence of a transition metal catalyst. On the other hand, ketones are reduced to secondary alcohols. Some chemists use sodium borohydride or NaBH4 in the reduction of aldehyde or ketone because this does not reduce carbon-to-carbon double bond. Now pause the video and try solving these problems. Addition of a molecule of alcohol to the carbonyl group of an aldehyde or ketone forms a hemiacetal. Its functional group is a carbon bonded to one OH group and one OR group. In forming a hemiacetal, the H of the alcohol adds to the carbonyl oxygen and the OR adds to the carbonyl carbon as shown here in the reaction of benzaldehyde with ethanol. Shown here is the hemiacetal formed by addition of one molecule of ethanol to cyclohexanone. Hemiacetals can further react with alcohols to form acetals plus water. The functional group of an acetal is a carbon bonded to 2 OR groups. Here is another diagram showing the reaction of a hemiacetal from cyclohexanone. All steps in hemiacetal and acetal formation are reversible. Now pause the video and try solving this problem. Another type of organic compound are carboxylic acids, which are also weak acids. Their functional group is COOH. All carboxylic acids react with stronger bases to form water-soluble salts. This is the equation where benzoic acid reacts with sodium hydroxide to form sodium benzoate. Sodium benzoate, a fungal growth inhibitor, is often added to baked goods to retard spoilage. Carboxylic acids also form water-soluble salts with ammonia and amines, as what is shown in the equation below. Now pause the video and try solving these problems. Reduction. The most common reagent for the reduction of a carboxylic acid to a 1-degree alcohol is lithium aluminum hydride or LiAlH4. Reduction of a carboxyl group with this reagent is commonly carried out in diethyl ether. Fischer esterification, named after Emil Fischer, is the treatment of a carboxylic acid with an alcohol in the presence of an acid catalyst such as concentrated sulfuric acid to give an ester. For example, treating acetic acid with ethanol in the presence of concentrated sulfuric acid gives ethyl acetate and water. there's the removal of OH and H in the reactant side to form water on the product side. In the next example, the alcohol adds to the carbonyl group of the carboxylic acid to form a tetrahedral carbonyl addition intermediate. In the case of Fischer esterification, the intermediate loses a molecule of water to give the ester.
Acid-catalyzed esterification is reversible, and at equilibrium, the quantities of the remaining carboxylic acid and alcohol are generally appreciable.
Now pause the video and try solving these problems. Decarboxylation is the loss of carbon dioxide from a carboxyl group. Almost any carboxylic acid, when heated to a very high temperature, undergoes thermal decarboxylation.
Most carboxylic acids, however, are resistant to moderate heat. Exceptions are those with the carbonyl group beta to the carboxyl group. They undergo decarboxylation by just mild heating.
For example, when 3-oxobutanoic acid is heated moderately, it undergoes decarboxylation to give acetone and carbon monoxide. Let's proceed to anhydrides, and this is their structure. Carboxylic anhydrides react readily with water to give 2 carboxylic acids. In the hydrolysis of an anhydride, one of the CO bonds breaks and OH is added to carbon and H is added to oxygen of what was the CO bond. Hydrolysis of acetic anhydride gives 2 molecules of acetic acid. Anhydrides react with alcohols to give 1 mole of ester and 1 mole of a carboxylic acid. One example is the reaction of acetic anhydride with ethanol to yield ethyl acetate and acetic acid. For this example, aspirin is synthesized on an industrial scale by the reaction of acetic anhydride with salicylic acid. Anhydrides react with ammonia and with 1 degree and 2 degree amines to form amides.
2 moles of amine are required, 1 to form the amide and 1 to neutralize the carboxylic acid byproduct. We show the reaction here in 2 steps.
First is the formation of the amide and the carboxylic acid byproduct. Second, an acid-base reaction of the carboxylic acid byproduct with the second mole of ammonia to give an ammonium salt. We'll add the ammonia of each equation, and we'll remove the carboxylic acid byproduct. And this is the final result. Let's proceed to esters, and this is their structure. Esters are hydrolyzed only very slowly, even in boiling water, but it becomes rapid when it is heated in aqueous acid or base. In the equation, we can simply see that hydrolysis of esters is the reverse of Fischer esterification. Hydrolysis of an ester can also be carried out using a hot aqueous base in a process called saponification, or the manufacture of soaps, which can be seen in this equation.
There are major differences between hydrolysis of esters in aqueous acid and base.
First, for hydrolysis of an ester in aqueous acid, acid is required in only catalytic amounts. For hydrolysis in aqueous base, base is required in stoichiometric amounts, which means 1 mole of base per mole of ester, because base is a reactant, not merely a catalyst. Second, hydrolysis of an ester in aqueous acid is reversible. Hydrolysis in aqueous base is irreversible because the carboxylate anion does not react with water or hydroxide ion. Now pause the video and try solving these problems. Esters react with ammonia and with 1 degree and 2 degree amines to form amides. As seen in this example, amides can be prepared readily from esters. Lastly, we have amides, and this is their structure. And they only perform one reaction known as hydrolysis. Amides require more vigorous conditions for hydrolysis in both acid and base than do esters. In this example, hydrolysis in hot aqueous acid gives a carboxylic acid and an ammonium ion. In this example, the products of amide hydrolysis in aqueous base are carboxylic acid salt and ammonia or an amine. Now pause the video and try solving these problems. Now that you have learned the different types of organic reactions, Let's review. Alkanes can undergo combustion and halogenation, while both alkenes and alkynes can undergo halogenation, hydrogenation, hydrohalogenation, and acid-catalyzed hydration. Benzene and its derivatives can undergo halogenation, nitration, and sulfonation. Alcohols undergo acid-catalyzed dehydration and oxidation. Both aldehydes and ketones can undergo oxidation, reduction, and addition of alcohols, while carboxylic acids undergo reaction with bases, reduction, Fischer esterification, and decarboxylation. Hydrolysis can be done by anhydrides, esters, and amides. In addition, anhydrides and esters can undergo reaction with ammonia and amines, while anhydrides alone can also undergo reaction with alcohols.
Well, that's about it. I hope you have learned a lot from this video. Until next time, stay safe. Bye!